Hello, and welcome to the third webinar from the Intelligent Transports Talks of the United Nations Economic Commission for Europe. This is the third in the series of talks that we are doing with regards to intelligent transport systems, and we're delighted to have you here today to hear from a distinguished panel of experts. My name is Jane Doherty. I am the Director of International Policy, Fuel Economy, and Consumer Programs at the National Highway Traffic Safety Administration at the U.S. Department of Transportation. I'm also one of the three co-chairs of the Intelligent Transport Systems Informal Working Group at the United Nations under WP29. And it is my pleasure today to welcome you to this series of discussions. 12 months ago, the United Nations enacted their contracting parties adopted a roadmap on intelligent transport systems, identifying a series of actions to prepare us for the future. This is the third session, which we will be discussing some of the actions that are proposed in the roadmap, where ITS is in 2022, and also we've discussed what we can do to ensure data security in the ITS context. But today we're going to talk about vehicle-to-vehicle communications and vehicle-to-infrastructure communications and the potentials that are there for us. You know, V2v ability to wirelessly exchange information about the speed and position of surrounding vehicles shows great promise to avoid crashes, to ease traffic congestion, and to improve the environment. But these will only be achieved when all vehicles can communicate with each other. So today, we're going to have an outstanding panel of experts in the field to talk to us about the latest news and what's happening in V2V communications. We're going to start with our first presenter. Dr. Steve Dellenbach is the Vice President of Automation and Data Systems Division at the Southwest Research Institute in San Antonio, Texas. He is leading research and development efforts in a number of areas, including intelligent transportation systems, unmanned systems, cooperative systems, aeronautical telemetry systems, space flight software, industrial robotics, manufacturing automation and process improvement, specialized sensing and sensor networks, advanced communication systems, embedded system security, smart energy, data analysis, simulations and training, interoperability standards and architectures. His division has approximately 185 staff members and performs approximately $50 million of research and development each year. Dr. Dellenbach holds a bachelor's degree in computer science from the University of Texas at Austin and a master's and doctorate's degree in computer science from the University of Kansas. We're delighted to have such an expert with us this morning to kick off our activities. And without further ado, Dr. Dellenbach, the floor is yours.
Thank you, Jane. I appreciate that. I'm also representing ITS America today. And what I would like to do is talk about some of the various programs that are going on with actual real-world development of ITS systems, or I'm sorry, of connected vehicle systems. So hopefully everybody can see my shared screen at this point. First of all, just from a perspective of where I'm coming at from connected vehicle is that we've been doing research and development for about 16 years in this area. We do a wide variety of development activities. You can see some videos of some connected vehicle systems that are exchanging data, trying to make vehicles safe. We do testing, we do pilot deployments, et cetera. And so my focus today is talking about some projects that are real or being deployed. As a side tie to all of this, we've also developed over 25 different unique automated vehicle platforms. About 2/3 of those are off-road type platforms and 1/3 on-road, and we use connected vehicle in most of those spaces. So the first project I want to talk about is a number of state Department of Transportations in the United States pooled their money together to look at how could we use the connected vehicle concept to improve work zone safety. As you probably know, it's one of the more dangerous things for road workers is to be working on a road that has active traffic. In the state of Texas, for example, the attenuator trucks that are used to protect a work zone, on average, 2 of those are weaker hit somewhere within the state of Texas. And so the concept of the study was, how could we get information from the Department of Transportation or the local government source that was actually doing the actual road work, that was actually funding it and getting out to the general public, because often there's not a communication mechanism from doing that. So the concept is, of course, is using something like a roadside unit, which would be portable and can be moved to the beginning of where the work zone is, and then the Department of Transportation staff could then enter that information into a local system and then can be broadcast out. Let me go to the next slide, which probably shows this a little more clearly. And so the idea is that somebody in the traffic management center or whoever is controlling the work zone would actually enter that information in, and then it could be deployed to an actual vehicle. This concept was demonstrated and is something that, as connected vehicle deployments are continuing, is being rolled out with them as they go along. Another program that's happening in the state of Texas, again, it's a big state, it's got a lot of different roads, is we have something called the Texas Triangle. If you look at this map in the upper right, and hopefully you can see my cursors, you have the Dallas-Fort Worth Metroplex up here in the upper part. You have over on the right-hand side the Houston area, and then you have the San Antonio area. Those 3 cities represent 3 of the largest population centers in the United States. And so it's something that we call the Texas Triangle down here, which is approximately about 800 miles or 1,400 kilometers of roadway. And so a number of partners have come together in trying to figure out, how do we improve moving freight along these corridors. This program was being led by the Texas Department of Transportation. You can see the number of performers that were down there. The thing that's not mentioned there is that there are several private shipping companies. One is a grocery store, which is very large in the state of Texas. It's the single largest grocery store in the state, as well as several different trucking companies are participating in this effort. And what we're doing is, those corridors all have various levels of ITS already deployed. So we already have sensors and signs and cameras, et cetera. And so we know quite a bit about the traffic conditions on there. So we are adding in now a connected vehicle component so that we can interchange data from the infrastructure to the trucks to provide them better information. Again, you can see down the left-hand side what's currently being integrated. This program is currently in process. Those in light blue have already been implemented, and those in dark blue are something that will either be done in the near term or in another phase of the program. Again, conceptually, what we're doing, though, is by getting this information into truckers, we can start improving their efficiency in both their routing and also the safety of the overall corridors that are going along. Again, real-world deployment. In the state of Georgia, the Georgia Department of Transportation is on task right now to implement about 1,000 different roadside units in the Atlanta metro area. That's a 6 million people population area. And what they're doing is they're putting SPAT, the signal phasing and timing. So they're tying into the local traffic signals to be able to provide that information to people that have connected vehicles in their cars. What that allows you to do is both potentially alter your speed to make your driving more efficient, less stopping and starting or less up and down in your speed. It also can provide you warnings that if somebody is running a red light. Again, one of the more difficult things to catch on your own is you're coming up to an intersection, but technology can tell you if somebody is running that. And so this is a significant deployment of connected vehicle SPAT technology. I know I'm kind of blowing through a bunch of these, but there's just a different number of things that have been done. Here's a program that is probably not been heard by a lot of you, but the Department of Energy, through ARPA-E, the Advanced Research Program area for ARPA-E, put out a program that's called Nexcar. And what they wanted to do was, could we use connected vehicle technology to reduce energy consumption by vehicles? And the idea is that if we knew what was happening with upcoming traffic signals, SPAT data, could we more optimally drive a vehicle? And so under this program, we first took a simulator and tied together from a simulator perspective, and then we started looking at the driving models of the actual vehicle. And we tried to look at how do you evaluate the power demand of the vehicle over time. And what we're looking at is things like what's the most optimal path. And what you find is sometimes if you go to a map application, you look at how do I get from point X to point Y, the shortest distance isn't necessarily the most fuel efficient way to do it. You may have more traffic signals in the shorter distance, you could have more traffic, et cetera. And then also the driving performance of the vehicle can really vary on how your fuel economy performs over that. So what we first did on this is we actually used a simulator-based approach where we used traditional transportation modeling tools out there, or traffic simulation tools, and using things like SPAT and other information from other vehicle. We first developed on a dyno of using a Toyota Prius to look at fuel efficiency. And at the end result of all of this is that there was a 20% increase in, or 20% energy reduction in a car. So essentially a 20% improvement in overall fuel economy. But the thing that was insightful about this program is, again, what modes were the most fuel savings, because we looked at things like routing, we looked at power split, because one of the things when you have a hybrid type vehicle, there's decisions that you make. When do you run the engine off battery or when do you run it off fuel? And interesting enough, those conditions, it's not always optimal to run your battery down to its least and then charge it up. There are times you actually may want to start charging earlier because, for example, if you know that coming up, there's a big hill coming up, you may want to start using an alternative energy source. This program was such a success for the Department of Energy, and it's one of the first times they ever used connected vehicle. It's been extended for 3 more years. Another area of research that's been worked on here in the United States is what we call Edge CV. If you're familiar with connected vehicles, one of the things that you know about it is tremendous amounts of data is gathered and it's generated. And so how do we process that data? And frankly, trying to communicate all that to a central source becomes troublesome because of the volume of the data. So how can we use edge computing, computers out at the edge at where the data sources are, to reduce that data in an intelligent fashion and only transmit the data that's actually necessary to make some type of decision to a centralized type source. Another program area that Jane mentioned earlier that you all looked at is cybersecurity. This is a big area of concern in when we use connected vehicles. How do you know the data is safe? I don't know how many people have seen the video on the lower right-hand side, but I think this is a fascinating example of how things like connected vehicle could be potentially misused. It was done by an artist in Berlin, and it was actually done sort of as an informal joke. But if you saw what he did in his wagon, so I think he put something like 50 different smartphones in his wagon, and he's pulling his wagon across a bridge. And if you look at the map view down at the bottom, you'll see he created congestion on the bridge. You can see the video of him. It's really almost no vehicular traffic at all, but all the mapping applications perceived that there was a problem with traffic. And so this whole area of cybersecurity and how are we making sure the connected vehicle data is being used correctly is something that's got a wide variety of research programs going on. Another concept in urban areas that has been developed here in the state of Texas is something called the Situational Awareness Hub, where you're actually using infrastructure data and transmitting that back out to cars using connected vehicle. And the concept behind the infrastructure hub is it can see omnidirectional, can see in all directions, so that you're approaching an intersection, you can get shared information. And it's not just about vehicles, but you can actually do pedestrian detection, bicycle detection, the whole vulnerable road user concept. And how that looks graphically, this was deployed in the city of San Antonio in South Texas. And you can see that the hub is picking up where the various humans are. Again, it's a bit of an odd situation. You have humans in 3 of the 4 intersections right now, and we're broadcasting that out to the local buses and the local cars, so that even though, for example, this pedestrian here is going against the green, you can see the green is going up and down in the picture, and you have a pedestrian crossing this way. So be able to broadcast that information out. Last couple slides is the within the United States, currently, Florida Department of Transportation is performing a development of a V2X data exchange platform. And the whole concept behind this platform is you have data coming in from a whole bunch of different sources, and how are you going to intelligently be able to manage that data to quantities that can be consumable in real time to be of use. In other words, you've got millions of basic safety messages coming in. How do you put all those together? How do you reduce those to actionable data and do something? So a bit of a word chart in a graphical form, but if you look over in the left-hand side of this, you have a whole variety of different type of data coming in. This exchange platform is sitting in the middle, and the concept behind it is all vendor agnostic. So if different companies want to participate in it, they can put data, and of course, then anybody can pull that data out. And so the idea is the data will move from the left-hand side, be transformed, be minimized and synthesized in the middle, and then at some point it would actually go out to the consumers that's depicted on the right-hand side of this. These are the type of graphs or the type of information. Showing it graphically is easier than probably putting it tabular, but the idea that different level types of heat maps could be provided to travel or to end sources to be consumed to help guide people with their using of connected vehicle data. So with that, I believe my time is up. I appreciate the opportunity to be able to speak to you, and I think we'll have a question and answer period later.
Thank you, Dr. Dellenbach. That was great. And we very much appreciate hearing where the research is going and all the good work that's underway in ITS America and at Southwest Research Institute. Thank you so much. And you're absolutely right. We're going to have several presentations. We have 3 more outstanding speakers, and then we will do a question and answer period at the end. So our next speaker, we're very fortunate to have with us today, Hillary Cain, a Vice President of Technology, Innovation, and Mobility at the Alliance for Automotive Innovation. Today, she's representing OICA, which is the International Organization for the Vehicle Manufacturers. Ms. Cain oversees policy development and strategy on technology and future mobility issues, including those related to automated and connected, driver privacy, cybersecurity, artificial intelligence, and intellectual property issues regarding vehicles. She is a recognized thought leader and frequent public speaker on policy issues impacting automotive technology and the future of mobility. In 2020, she was recognized as a rising star in the automotive industry by Automotive News for her work on the forefront of emerging technology policy. Prior to joining the Alliance for Automotive Innovation, she spent 8 years as the Director of Technology and Innovation at Toyota, where she led policy development issues and advocacy on technology policy matters. She previously worked in the U.S. House of Representatives, serving as the Staff Director on Technology and Innovation, their subcommittee and council on the Committee of Science, Space, and Technology. And also, she was the Legislative Director on Ways and Means Council for individual members of Congress. She holds a JD and an MA, a Master's in Administration in Public Affairs from the University of Texas, and a Bachelor's of Arts degree in Political Science from the University of Washington. Today, we are delighted to have Hillary Cain as our presenter. Thank you, Hillary.
Thank you, Jane. Let me get my presentation up here and we will get this party started. All right, great. Hopefully everyone can see my screen. So thank you, Jane, and thank you, Steve, for that fantastic overview of all of the potential for V2V and V2I technology. I think we're all probably on the same page in recognizing what a tremendous potential there is here and share our goal of getting this technology widely deployed throughout the world. So as Jane said, I'm Vice President of Technology, Innovation, and Mobility Policy at the Alliance for Automotive Innovation. The association, I want to give you a little bit of background. We were formed just in January of 2020 as a merger of 2 pre-existing associations, the Alliance of Automobile Manufacturers and the Association of Global Automakers. So those 2 associations came together to form the Alliance for Automotive Innovation. We are the primary association for the auto industry in the United States. We advocate for government policies in the United States that support the auto industry and its transformation to a cleaner, safer, and smarter future. We represent the entire automotive ecosystem. We represent the automakers that make up 99% of the U.S. new vehicle market. We also represent automotive suppliers and technology companies that work in the automotive space, particularly sort of automated vehicle startup companies. As Jane mentioned, I am here representing OICA. The president of my organization, John Bozzella, was elected president of OICA in November of 2021. And so we are very excited for him in that role and for us to be able to work with our colleagues throughout the world on important issues such as this one. So I mentioned a moment ago that my association focuses on government policy in the United States. So I'm going to use my time today to talk to you about what I know and give you all an update on the status of government policy in the United States on V2V and V2I. Now, I think this is particularly relevant because, at least as the United States goes, government policy continues to have significant impacts on the deployment of V2V and V2I. The last 9 years have proven to be very challenging environment for auto companies and other stakeholders to deploy V2V and V2I in the United States, and that is largely because of government policy. And I think there are also broader implications outside of the United States because this technology will require coordination and collaboration between the private sector and government. So there are two agencies within the United States that have direct impact on V2V and V2I deployment in the United States. The first is the Federal Communications Commission. This is the agency in the United States that manages radio spectrum. We will talk a little bit in a moment why that's important. The second agency is the U.S. Department of Transportation, which oversees motor vehicle safety in the United States. So let's first start with the Federal Communications Commission. As folks probably are aware, the ability of anything to communicate wirelessly with anything else requires access to radio spectrum. So for V2V and V2I technology to work, there needs to be some spectrum, some radio spectrum on which it can operate. So in 1999, many years ago, the Federal Communications Commission allocated 75 megahertz of spectrum in the United States in what is known as the 5.9 gigahertz band for V2V and V2I using dedicated short-range communication protocol, which is a communication protocol that can support V2V and V2I communication. This set off extensive work by industry and other transportation stakeholders to develop and prove out this technology. So there were years of research and development and collaboration and validation activities. And right at the time that some larger scale pilot programs were proving out the value of V2V and V2I technology, including for collision avoidance, for crash avoidance purposes, the Federal Communications Commission started to explore the possibility of reallocating some of the spectrum away from V2V and V2I and for other purposes. So the industry and other transportation stakeholders spent 7 years, 7 long years trying to convince the Federal Communications Commission to maintain all 75 megahertz of spectrum for V2V and V2I. This period, the 7-year period, was of uncertainty, really, uncertainty over whether the Federal Communications Commission would take some or all of the spectrum away from V2V and V2I, really chilled V2V and V2I deployment in the United States. I think companies felt that there was a significant risk in deploying this technology and then possibly having the Federal Communications Commission take away some of the spectrum, maybe even the spectrum that was being used, or that changes to the spectrum could impact the performance of the technology. So you had a 7-year period where there was not much deployment in the United States. Unfortunately, despite the efforts of industry and other stakeholders, these efforts to convince the Federal Communications Commission to preserve all of the spectrum were unsuccessful. And in 2020, the Federal Communications Commission moved forward and decided to reallocate 45 megahertz of spectrum away from V2V and V2I. So that 75 minus 45 means that there was 30 megahertz left. And then they also specified that V2V and V2I were to use a different communication protocol going forward, a communication protocol called C-V2X. So what does this all mean for V2V and V2I deployment in the United States? A few points here. One is that in addition to taking away 60% of the spectrum, the Federal Communications Commission also set emissions limits for the technologies that would now be using the lower part of the band, the part of the band that they took away, at a level that's likely to cause harmful interference to V2V and V2I communications in the remaining 30 megahertz. And this raises very real questions about the usability of the spectrum for safety critical applications such as crash avoidance technologies, which is, I think, one of the most promising use cases. And this obviously creates some challenges for auto companies, for example, that are looking to deploy if they can no longer maybe use this spectrum for crash avoidance. The second is that less spectrum means that the range of applications that can be offered will be less. You can do less with 30 megahertz than you can do with 75 megahertz. And so if the opportunity to offer a number of applications is no longer available, there is less incentive perhaps for auto companies and other stakeholders to move forward because there will be fewer benefits potentially for consumers. And the third point is the transition to C-V2X creates some challenges that we need to work through. One is that some automakers have focused their R&D efforts so far on DSRC, and now those companies must shift to C-V2X if they want to move forward. And that means maybe some new R&D, some new testing, some new validation for them. The second is that there is some infrastructure that's already out there that is using DSRC, and that infrastructure must now also transition to C-V2X if it would like to continue to be a part of the network. And the third thing is that the Federal Communications Commission actually has more rulemaking that they have to do here. When they issued the rule in November of 2020, there's two phases to the rule, and they only did phase one. The first phase was the reallocating the spectrum away from V2V and V2I. And also telling DSRC technologies, or DSRC, that it had to get out of that lower part of the band within a certain amount of time. What they did not do, however, is set the rules for how C-V2X can actually get access to the spectrum. So we have this very strange situation now where companies are not going to be supportive of moving forward with DSRC because they know they will not have continued access to the spectrum, but C-V2X can only get into the band through a waiver or special temporary license. So it's created a situation where we might sort of nobody has access to the band right now. The next agency that I want to talk about is the U.S. Department of Transportation. The U.S. Department of Transportation has obviously been very excited by the safety and collision avoidance potential of this technology. So in August of 2014, they initiated a rulemaking to require all future vehicles to have V2V technology. There was quite a bit of industry support actually for this technology, for this rule. It is a cooperative technology, which means that the higher the fleet penetration, the better. We can realize the safety benefits more quickly, the more vehicles that have the technology. In 2017, They did decide to move forward in the final days of the Obama presidential administration with issuing, or actually proposing, a new V2v safety regulation. Then within days, there was a change in the administration. The Trump presidential administration came in, and that rulemaking was paused. And as we sit here today, the rulemaking is still paused. There's no work going on as far as we know on it, but it has not been formally withdrawn. So last thing here I just wanted to mention, and then we'll wrap up and move on to the next speaker. Sorry, I'm finding my notes here. Okay, so I'll go back to this and finish one last thought here. So it's I mentioned this because this does impact the willingness of auto companies to move forward with this technology. So if there is a mandate, if there is a regulation that will be issued, companies will likely want to wait to see what that regulation looks like to make sure that the technology that they deploy complies with the regulation. So what's happened here is between 2014 and 2017, you had auto companies waiting to see what the regulation might look like. And then since 2017 to today, you've had companies wondering when maybe there's a chance that the Department of Transportation will move forward, even though it's unlikely that they will, but because they have not formally withdrawn it, there's still a chance that maybe that they will move forward. And so there's still sort of this nervousness about moving forward, just in case there will be someday a regulation that may impact a company and the technology that they would have on their vehicle. So last thing, just to summarize, there are a number of things that I think that the US government can do to help support V2V and V2I technological development in the United States. The first is that the Federal Communications Commission can resolve these harmful interference issues so that the 30 megahertz can be used for safety critical applications. The second is that they can allow C-V2X to access the band while they do their phase 2 rulemaking rather than keep it on hold until the rulemaking is complete. The third thing the Federal Communications Commission can do is allocate more spectrum for V2V and V2I to accommodate additional applications and the evolution of the technology, the next generation communication protocols. And the fourth thing the Federal Communications Commission can do is to provide reimbursement costs to infrastructure owners and operators that are transitioning to C-V2X. There's a few things that we think the US Department of Transportation can do. One, they can proceed with the safety regulation, or they can formally withdraw it. They need to do one or the other to provide clarity and certainty to the industry. The second thing the US Department of Transportation can do is collaborate with stakeholders to prioritize V2V and V2I applications in the remaining 30 megahertz. With less spectrum, I said there's less you can do. We need to sort of reach consensus on what the things are that we can do with the limited spectrum. And then the last thing that the US Department of Transportation can do is provide additional funding to help build out V2I infrastructure. So with that, I will wrap up and turn it back over. Thank you so much.
Thank you, Hillary. We really very much appreciate the presentation. This morning you've heard a lot, or today you've heard a lot about what's happening in the United States. But WP29, the World Forum, is a global forum, and there's so much happening elsewhere. We want to shift our focus right now to Japan and all of the activities that are happening in Tokyo. So with that, our next presenter is Mr. Masato Minakata, who is part of the Interministerial Project of Strategic Innovation Promotion. Mr. Minakata is a member of the International Cooperation Working Group working on the Strategic Innovation Promotion Automated Driving for Universal Services. He's an expert in the field. He has started his automotive industry career at the Toyota Motor Company in Japan in 1986 in the Electronics and Engineering Division. He's worked at the Toyota Technical Center in the United States. And since 2016, he has worked in the Vehicle Safety Planning, Research and Development and Engineering Managerial Division at the Toyota Motor Company in Japan as a Grand Master. a member of SAE and very well respected in the field. We're delighted today to welcome Mr. Minakata to our forum. Minakata-san, the floor is yours.
Thank you, Jen. Can you see my presentation material? Jen?
Yes, we can. Thank you so much. Looking forward to it. Thank you.
Okay, I will start. So thank you for giving me a time to report. I'm Masato Minakata, working as a field operational test planning leader at the SIP ADAS. Today, I would like to report about the FOT, Field Operational Test in Tokyo Waterfront area, conducted by SIP ADAS project. ADAS means Automated Driving for Universal Service. SIP ADAS aims to solve various social problems by spreading automated driving system as soon as possible. We have to cooperate in order to overcome the common hurdles because automated driving system realization is a drastic change of driving subject from human driver to system. In SIP ADAS, we tackle various issues such as research and development, regulation reform, public acceptance creation, international cooperation with government, industry, academia cooperation. Regarding technology, we focused on the cooperative themes. For example, establishment of dynamic map, safety assurance, cybersecurity, human factors, and so on. As you all know, traffic environment information in autonomous driving system is very important. In order to realize highly safe driving support and autonomous driving, the vehicle collects and monitors information around itself with various sensors. But the information that can be collected by the sensor of their own vehicle is limited. In order to realize more advanced safe driving support functions and to realize autonomous driving under various road environment conditions, more traffic environment information, such as highly accurate 3D map data and signal information is required. Considering that it is necessary to provide information from infrastructure, we have been based on the concept of dynamic map as a collaborative area since the first phase of SIP project, and based on the ever-changing digital traffic environment information based on certain rules. In line with Society 5.0, which the Japanese government advocated, industry, academia, and the government are working together to develop technology in a collaborative area.
Sorry,
In Japan,
San?
as you know, an information provision service using DSRC wireless communication technology has already started in 2015 using the frequency band assigned to ITS application in Japan. At SIP, we are working on research and development and the practical applications of ITS technology necessary for realizing the advanced safety driving support and the infrastructure coordinated autonomous driving system while making the best use of these assets. One of the important themes that we have consistently worked on in SIP ADAS project that started in 2014 is research and development related to the development and operation of traffic environment information. From the establishment of static infrastructure information in the first phase of SIP, we are working on creating a mechanism for the development and operation of dynamic traffic information in the second phase of SIP from 2018. Among the activities, field operational test in the Tokyo waterfront area plays an important function as a place to openly confirm the effectiveness and identify issues through information generation and distribution in the actual traffic environment. Here, I would like to explain the outline of the Tokyo waterfront area field operational test that started from 2019. As explained on the previous page, the aim of the field operational test is a place that can be used for research and development of open autonomous driving, as well as functioning as a milestone for practical use in an actual traffic environment. In the FOT, we set the themes according to the characteristics of each place in the three areas of the Tokyo waterfront area. In the end, 29 institutions such as the domestic and foreign autonomous automobile manufacturers, system suppliers, venture companies, universities participated. In the second phase of the SIP, Tokyo waterfront area field operational test, we are working on a demonstration to utilize dynamic traffic environment information through wireless communication. For example, we conducted a field operational test in the Odaiba area to realize autonomous driving using signal information by narrow-range wireless communication with the eye, using a dedicated frequency band assigned to Japanese ITS applications. We don't have much time today, so I would like to briefly report on the result obtained from FOT. In the Odaiba area of Tokyo, wireless communication equipment was installed at 33 intersections traffic lights to distribute current signal information and remaining seconds information. Participants conducted the field operational test under various courses, directions, time zones, and weather environments, and confirmed the validity of the information. As a result, we have demonstrated that the signal information via VTI can be used stably even in an environment where it is difficult to recognize the signal by the onboard video sensor. It was also demonstrated that the signal remaining seconds information is effective in avoiding the dilemma zone when passing through an intersection. From the above, it was concluded that the provision of signal information by wireless communication is extremely effective in expanding the operational design domain for highly automated driving on general roads. In addition, many participants have commented that this information can be used not only for autonomous driving vehicles, but also for general drivers. Furthermore, in order to spread autonomous driving widely, it is necessary to prepare this information, this information distribution environment as an area, not at each intersection. Therefore, we have decided to newly conduct FOT by Wide Area Public Network V2v. Currently, SIP is researching a new information generation and distribution architecture via Wide Area Public Network V2v with a view to practical application. and is proceeding with FOT by constructing an experimental environment in the Tokyo waterfront area. 22 organizations from Japan and overseas have announced their participation in the 2021 field operational test with this new theme. And they have already participated in the working group, which is a place for exchanging various opinions and information. Here is what SIP is aiming for through field operational tests in 2021. By providing similar information on a regional basis, we have expanded the area to which advanced driving support and autonomous driving can be applied. Contribution to early preparation in anticipation of heavy rainstorm, creating a mechanism for utilizing probe information. Taking as an example, a lane change with a margin by predicting a traffic jam lane. Emergency vehicles have also been converted into the connected vehicles, and the information is used to alert people and realize autonomous avoidance control. The above are just a few of examples of the infrastructure coordinated autonomous driving that can be realized by utilizing traffic environment information. But there are various possibilities if a mechanism for widely utilizing the traffic environment information is established by V2N. SIP is also working to develop a technology roadmap for how to communicate between infrastructure and vehicles. In formulating the roadmap, not only the automobile industry, but also industry, academia, government collaboration, and the ICT industry are collaborating to conduct research for the future. We investigate the function of infrastructure coordinated autonomous driving using communications and summarize it as 25 use cases. We have formulated communication requirements and draft communication methods to realize use cases. Currently, we have just completed compile a roadmap related to the communication methods based on the social implementation schedule of use cases. This is summary of today's report. In SIP autonomous driving, we confirmed the effectiveness of signal information distribution by V2I and decided the specification of signal information distribution from infrastructure that meets the requirements for automatic driving through the Tokyo waterfront area FOT. In fiscal year 2021, we are working on a new field operational test using V2N with the aim of putting into the practical use the expansion of the dynamic traffic environment information utilization scheme. Through industry, academia, government collaboration, SIP is also working to formulate a roadmap for communication technology. The final report will be published this year. Field operational test driving and data collection are scheduled to end in February. For an overview of the Tokyo waterfront area operational test and future information, please refer to the SIP official site. Finally, there is an international collaborative activity by SIP ADAS. Since the start of the SIP ADAS project in 2014, we have held a workshop every year where government officials and experts from Japan and overseas gather to exchange opinions. Last year's 7th workshop was held online due to the influence of the COVID-19, but it was a great success with the speakers from 11 countries. and the online participation of people from 23 countries. As we enter the final year of SIP, we are preparing to hold it from October 11th to 12th this year in Kyoto. We hope that everyone will join this workshop in Japan. That is all my report. Thank you for your attention. Thank you.
Thank you so much, Minakata-san. That was wonderful and so informative of the progress that's being made, the work underway, and look forward to Kyoto and all the progress that's going to be reported. But you're showing how we all need to work together to make this happen. Thank you so much. We very much enjoyed your presentation.
Thank you. Thank you, Jen.
Right. And I want to make sure everyone is aware all of the presentations will be available afterwards online. We're looking forward to sharing those with you. And after our next speaker, there will be a question and answer period. So start thinking of your good questions to ask our distinguished panel. Our final panelist today, and we're very excited to have him, is Uwe Prislan, who is the head of the Automotive and Mobility Solutions at Nokia. He's representing today in his position as the vice chair of the 5G Automotive Association. The association is a global cross-industry organization of companies from the automotive, technology, and telecommunications industries. They're working together to develop end-to-end solutions for future mobility and transportation services. The organization itself was created in September 2016, and it unites a large number of members from Audi, BMW, Daimler, Ericsson, Huawei, Intel, Nokia, and Qualcomm. We're delighted to have Mr. Prislan with us today and to talk to us about the future in a connected world. So with that, Uwe, the floor is yours. Thank you.
Thank you very much, Jane, for the introduction, and I'd like to welcome everybody to the next and final presentation today. As said, I am representing the 5G Automotive Association, and at the beginning I want to give you a few more details about that association, which was founded 2016, as Jane mentioned, and the main objective was to bring automotive industry and telecommunications industries together. To bridge the two segments of our society in order to address the connected mobility needs, and in particular to move on or to focus on safer, more efficient and environmentally sustainable services in the ITS domain. So that was the objective 2016, and at that time 8 companies, which were mentioned by Jane, founded the organization, and today we are more than 120 members from all parts of the world, with the top OEMs represented in the organization, also the mobile network operators, smartphone vendors, and many, many different technology providers. Let's take a look at what we've been focusing on and working on. First of all, I would like to convey with this slide 2 messages. The first one, the board represents the organization, and it shows that all the important segments are well represented at the board, not only from a technology point of view, but also from a geographical point of view. So we have the main regions as part of our organization, also leading the organization. And the second important point is the structure of the organization reflects the work areas which are required, to say it with one sentence, to make it happen, to bring connected vehicles onto the roads. And we focus on obviously use cases. What are the use cases? What are the requirements related to those use cases, the KPIs of those use cases? What is the right architecture for the solutions? How to test? What sort of certifications are required? That's another working group. input into standardization organizations, acknowledging that it's not our job to create standards, but to provide the input or to make proposals to the standardization bodies. And spectrum topics are also very important. Hillary talked already about the role of the spectrum in this particular segment. Another area, how to go to market, what are business and cooperation models in this segment. And we know that different industries need to come together to make it happen. Another area, work group 6, is dedicated to regulatory and public affairs topics. And here we have seen already that the regions have quite a lot of differences, and that's why we allocated subgroups for the different regions. And last but not least, security, privacy are extremely important matters in the context of connected vehicles. So that's a bit of an overview about the organization, which is working on many different work items. And I hope it has become also clear our focus is to make it happen, so to take it to the road. And in the next minutes, I will be talking about what is going on around the world with respect to hitting the road. And let's quickly start with a brief recap on the technology. It has been mentioned and that we have short-range communication. It's a very important part of the technology, allowing the direct communication between the vehicles without the network, or between the vehicle and the road infrastructure, or even later on, we expect also between the vehicle and, for instance, smartphone or pedestrians or bicycle riders. The other important element is the network-based communications. So from the vehicle via the network to the cloud, and via the cloud to other vehicles or to road infrastructure, or also, and that is very important, to so-called vulnerable road users. And in most cases, these are traffic participants which have a smartphone. And there's no doubt we need and we want to include those traffic participants into the entire system as well. So it is about really the combination of two communications technologies, the network-based and the direct communications, and their complementary approach is necessary to really improve the mobility ecosystem. Now let's look at more the network-based communications, what's going on. You all know that we are now seeing the 5th mobile network generation being deployed in more and more countries. The rollouts are happening. And what is remarkable that many countries and the regulators in those countries associated with the licenses to operate 5G networks, also obligations to cover roads and other transport corridors. Unfortunately, different countries have taken different decisions. Some countries have put very demanding coverage obligations in place. Germany is an example, Greece fairly similar. Others have less demanding obligations, but also have clear objectives to cover the main transport corridors of their countries. And that's not just in Europe, we see that also in other parts of the world. So, and that's a prerequisite. Road coverage is a prerequisite for using the network-based communications. And if we look at what's going on with respect to vehicles we see on the roads today, then more and more of the new vehicles are connected via the network today. And now we see, first of all, the first vehicles being connected via the 5G networks. It started in China. Now we have also in Europe the first 5G connected vehicle, which is a BMW. And we see more and more vehicles also equipped with short-range communication. And that's in particular happening in China. And we will come back to that in a few minutes. Another trend which we see is that the connectivity which most of the new vehicles have now via the network is not just being used for telematics or infotainment, but more and more also safety-related applications are being introduced step by step. And different car manufacturers started with different safety-related or hazard information distribution within their fleets. And clearly, now the next step is to make it happen also across the car manufacturers. Europe started an initiative to make it happen with different car manufacturers, different road operators from different countries, and also service providers like Kia, TomTom are involved in this as well. So we see that as an important step to extend the scope of those applications. Another trend which we see is using smartphones. So this is a common now gadget which most of the people use today, and clearly this can also be used to improve safety while driving. And we have some good examples in the Netherlands. The Talking Traffic project has been ongoing for quite some time, several years. Many users are using applications in their vehicles, and together with a clear trend to digitalize the road infrastructure, to introduce intelligent traffic lights and other digitalized interfaces to road infrastructure, that makes it possible to provide useful information to drivers while driving on the roads. Similar approach in the US, travel safely application is available. It can be used in Georgia, and I think Steve mentioned in his presentation also the infrastructure rollout in Georgia, and this can also be used, or the digital infrastructure provides benefits to smartphone users as well. But clearly, as we mentioned, both communication technologies are complementary, and that's why many road operators are looking into deploying roadside units. In Europe, we have examples for both technologies, and Europe is a specific situation, which I will explain in a second. And China is also going ahead full steam with equipping motorways with roadside units. Let me use a few words for Europe. In most of you are aware that we have two short-range technologies, and both technologies can be used in Europe, and that's why one of the approaches to use the technology is also to deploy dual mode RSUs to address this topic. Now let's look more at short-range communications. But before we go to that, one slide showing some of those examples, how car manufacturers use the network connectivity of their vehicles to support hazard information distribution within their fleet today. You see examples from Ford, Volkswagen, slippery roads warning, Mercedes-Benz, pothole detection, and that's only one example. There is an entire list of different hazard situations which are detected by the vehicles, sent to the OEM's cloud, and then the cloud distributes it to other vehicles of these car manufacturers. Skoda did something related to wrong way driver warning. Volvo introduced this concept some time ago. But the network is also used to support, for instance, the closer use case, which has also a quite interesting impact on traffic efficiency, and last but not least, also potential on reducing pollution. And Audi is doing this in several cities in the US, also in Europe, and it's also being implemented over the network. But now let's go to short-range communication. And China is clearly leading that trend today with a very early decision to focus on CV2X as the technology. And during the last 2 years, we have seen many car manufacturers, Chinese car manufacturers, but also car manufacturers which are in cooperation with others in other parts of the world to release already vehicles onto the road, which include short-range communication. And this number will grow quite substantially over the next year, 2 years, and that's what we expect to happen. So we will also see that the impact of the technology being deployed. And you know that in China there are very large scale proof of concepts going on with thousands of vehicles being involved, and also many of the crossings in the city equipped with roadside units to support the use cases, which are shown here on the next slide. Quite a lot of V2v and V2I oriented use cases. So that is something which we monitor as an organization quite carefully, because we want to see what is the impact. And that's also a good topic to come back. What is the impact of the technology? We understand that the penetration of the technology amongst the vehicles on the road is a very important factor. And that is why we need a quick deployment of those vehicles equipped with the technology, otherwise we will not see the benefits. It is the combination of the digitalized road infrastructure and the capabilities of the vehicles to make those use cases happen and to see the benefits of it in the field. Let's quickly take a look at the situation in the US. I don't think that I need to say a lot, because Steve and Hillary talked about the work which is going on in the US. But I would like to mention that Ford already in 2019 made a clear announcement that the technology, the short-range technology CV2X, will be in the vehicle beginning in 2022. So hopefully this year we will see it, given certain conditions, of course. But it looks like, as Hillary explained, that now we seem to be on the right track to make it happen in the US. And we see other car manufacturers now to be active and to make sure that we see the technology not just in proof of concepts or research projects, but we want to see it in the vehicles which are on the roads and everybody can buy. So there's quite a lot of activity going on. And just to mention here the example on the right, to protect, for instance, pupils with the right technology in the school buses and also then the vehicles. So what we see is a strong momentum around the world to get the technology onto the road. But let's look a bit into the future. 5GAA published a roadmap in 2020 about the deployment, the mass deployment of CV2X use cases. It's a very complex picture. We acknowledge that. And I would like to highlight 2-3 points. First of all, it shows quite well how different generations of the technology, the 3GPP technologies of 4G and 5G play a role in the deployment of those use cases. Naturally, today, the vehicles which are on the roads, they have the 4G equipment, except the few new which I mentioned earlier. And we see this hazard information distribution already. It started, by the way, in 2016. That's on the roads. And in China, it's also being used using short-range communication. And the explanations here is important. So a blue frame means the use case is implemented using direct communication, and the blue colored box means the network is the main communication instrument to support the use case. And we see, looking into the future and looking into use cases which are needed to support automated driving, like group starts, cooperative maneuvers, sensor sharing. These use cases clearly will need 5G to be in place, and it is a combination of 5G short-range communication, 5G V2X, and network-based communication. So, but there is a lot of work to be done in the ecosystem to make those cooperative driving use cases really a reality. And that is one of the areas 5GAA wants to focus on to help making it happen. There are still a few roadblocks, and it's regulatory topics. Spectrum was mentioned, but also in the standardization, there's still some work to be done to make those use cases happen, so that we will be able to see these cooperative driving use cases in 2026, 2027, or 2028. And with this, I want to finish. I hope I have demonstrated two main things. The first one is it is a combination of short-range and network-based communications, which we need to really see the benefits of the communications technology in the future. And the second point is it's happening. It's happening on our roads. There are differences between the geographies, but we see it happening. The vehicles get equipped with the technology, and so we are optimistic that we will see more and more vehicles really using the benefits of those use cases everybody is talking about. And on this, I would like to thank everybody for your attention, and let's see the questions. Thank you.
Thank you so much, Uwe. That was fantastic. And your report about what's happening in different parts of the world was just fascinating. So thank you so much for that. It's encouraging to see how much work is happening all over. And you know, so much has been done already, but we have so much more work to do together. So we look forward to hearing more from you and from our panel as we move forward in our work at the United Nations. I understand there are some questions, so looking forward to hearing from some of you. But I apologize, I'm having some challenges with the questions, so hoping to be able to pull that up. Okay, so our first question for our panel, and I want to thank you all. You all did a fantastic job explaining to us where we are and where we're going and what the challenges are in front of us. But first question for you all, is there a potential gap in that we can specify the vehicle technology, but how do we ensure that the vehicles can link to the infrastructure? technology seamlessly. And if we get it wrong, then we risk delaying the benefits for years, given the life cycle of new vehicles and the high costs. So anybody want to tackle the question of how do we do this so that we build that infrastructure technology seamlessly and we try to do it right the first time? Does anybody want to tackle that question based on your experiences already? I know there's a lot of good work going on in Tokyo, a lot of good work happening in Europe and the United States. So anybody?
Maybe let me start. It's Uwe speaking.
Wonderful.
First of all, I would like to stress the prerequisite, and that is the digitalization of the road infrastructure, which means data need to be available at interfaces in order to also provide services relying on that data. So that's the fundamental prerequisite. To have this in place. And then we have two ways of connecting to the infrastructure. One is the direct communication, and examples were demonstrated today during the presentations, and we see that is possible, and China has also some initial scale on that, but there is also the other alternative to do it via the network to reach a much higher number of vehicles with some of the use cases which can rely on network connectivity. So it is about both and to use both communication technologies for the right use case. And I stop on this.
Jane, this is Steve, and I can just offer up that I think one of the connectivity challenges, we often think of urban areas when we talk about this technology, and I look at, many of the slides I presented, they were always in cities. Yet our freight corridor that we're implementing, there are periods of 1 to 3 miles that have zero communications infrastructure. I mean, if you're talking on your phone stops, and so the whole paradigm, even extending this to automated vehicles, and that's going to be the backup, is that people will call into an automated vehicle and manually control it. We don't have 100% communications coverage in all areas. So, again, I'm not a telecommunications provider, and I know they can solve that problem, but there's a cost involved with all of that. So I think that's one of the other things we need to consider in all of this is never forget rural, because there's a lot of lives lost in rural applications that could be saved.
That's a great point, Steve. Absolutely. And I know it's something that we're struggling with in the United States, and I'm sure all over the world. So there's more work for Uwe and some of his partners in 5GAA to continue. So we look forward to that too.
This is Hillary, if I could jump in too. I mean, I agree completely with everything that's been said so far, but I more fundamentally agree with what the questioner was getting at, which is, in order for this to work, in order for all of the benefits to be realized, it is going to require extraordinary coordination between the automakers, the infrastructure owners and operators, and the government. This is really the cooperative nature of this technology requires a level of coordination that I don't think we've ever really seen before when it comes to vehicle technology. And anyway, so I just wanted to go back to what the participant, the question, and the foundation, the fundamental sort of foundation of it, which is we need to be working together in a way that like I said, we've never seen really before, I think.
Mm-hmm. Great. Well, it was a good question, and it came from my co-chair from the Intelligent Transport Systems Informal Working Group, Ian Yarnold, who is a master at bringing everyone together and getting everyone to work cooperatively together at the UN. So it was a great question, and thank you, Ian, for that question to get us started. Our second question for the panel is from Russ Greger, and he's asking, it seems that V2V and V2I are already addressed in various countries. Is there a role for harmonization bodies? Or can this be all run on a voluntary basis on telecommunications standards, but without regulations? So who would like to take that question first? Great question, by the way, Ross. Thank you. Hillary, I'm going to start with you if you don't mind. I thought your presentation was great, and you talked about some of this already. What are the rules, and do you see this as a voluntary issue, or do you see this as a need of government infrastructure and government regulations?
Yeah, so maybe where I can start is I think, there's sort of two pieces of this, and I think I tried to cover both of them in my presentation, which is I think we don't necessarily need regulation throughout the world to support V2V and V2I deployment. I think it can be done on its own. I think there is desire and momentum to do so. But where we cannot do it on our own is with respect to the spectrum piece that we've touched on. Spectrum requires, I think, universally throughout the world, the government to make an allocation. And so if the government chooses not to allocate it sufficient spectrum, or chooses to allocate spectrum in a way that creates challenges for V2V and V2I deployment, there will be real consequences for the deployment of the technology. So regulations not required generally for V2V and V2I, in my opinion, but spectrum allocations controlled by governments is a fundamental component of this.
Thank you.
Jane, I can jump in and offer up. I think one of the things I worry about in not having any regulation is, go back to the classic beta versus VHS paradigm. Did the better technology win back then? And, a lot of people would argue that beta was a better visual technology, but VHS got the commercial technology. So I worry a little bit if this industry doesn't have regulations, the elephant, the biggest guy is going to win. The biggest company out there is going to win. And what's it going to do to potentially smaller companies? I'm not saying it will happen. I think it's something we need to be sensitive to, that, sometimes letting the market decide the winner isn't always equitable. There's some big companies out there that I know in America right now, people are really frustrated with some of the big monster companies, and they don't like them. Is that the right way to do this? I'm not convinced it is. So maybe regulation might help that some.
Right. Thank you, Steve. Yeah. Minakata-san or wait, anybody?
Yeah, maybe if I add one thing to that, it was said, is standardization sufficient? I would say definitely not. It's a prerequisite. There's no doubt about to standardize the technology, but the existence of these industry organizations show that it's more than just standardization. Yeah, we mentioned regulatory aspects. There are also go-to-market or cooperation models, because it is absolutely clear, and it was mentioned, this is about different parts of the society or segments need to work together. And it's even more challenging because private industry and in many countries, public authorities, road operators or public authorities, they need to work together to make it happen. And that itself is a challenge. And here cooperation is vitally important.
Great, thank you. I think we have time for one more question. So this is a question for all of you. How can regulators help to get this safely implemented and provide hazardless services to all road users? So tell us, how can we do our job more effectively? Anyone?
Well, I'll jump into the fray for.
Go ahead, Steve.
And maybe I'm going in too deep of water, but what's the incentive for people? To me, that's the if the regulation is there, if there's an incentive, then companies will do it. So for example, if in order to sell their product, it has to meet a certification, then I think they're going to be, more willing to jump on it. There's got to be I don't know. I guess what I'm trying to say is I think there has to be a reason for people to want to do this, and if a regulation helps that. Safety itself doesn't normally sell. When you go talk to a car dealer, people will buy a high-end stereo before they buy a high-end safety system. And, historically is showing that. And so how do you get the consumers to understand that there is a safety is a challenging because it always happens to somebody else. It never happens to me. And, I don't know how you break that. And maybe regulation would help. Again.
Steve, I think that sometimes we do our job so well and that people just expect, the customer expects that car to be safe, right? So they're not going to expect that they have to pay more for additional safety issues. Those are
Exactly.
basic in the car so that they can spend more money on that radio. It's good that there's confidence that their government regulators and the industry have worked together to ensure the safety of that car. But I think we've got to figure out a way. You're absolutely right. The incentive, the carrot, where's the carrot to make the industry work with the government and the safety advocates to continue to improve that infrastructure, to build that infrastructure for V2V and V2X systems. So that's a really great point.
I'll just jump in and I will say, at least from the automaker side of things, and I think we saw a slide earlier today, perhaps, I think we did, that mentioned that the automakers a few years ago did come together and make a voluntary deployment commitment to deploy 5 million V2X devices in the United States over 5 years. And I point that out only because there was, the sense I'm getting from the member companies that I work with, have the privilege of working with every day, is a very, very, very strong desire to bring this technology to the global market and the US market as well. And, not needing to necessarily be told to do it, desiring to do it, recognizing the tremendous benefits that there are. But going back to sort of the what can government do? That's what my whole presentation was about, really, is the challenge we have right now in terms of the spectrum policy in the United States that can support what it is that the automakers want to do, and I think what a lot of infrastructure owners and operators want to do. So the two things that the government, at least in the United States, can do is resolve the harmful interference issue, make sure that we can use that spectrum for safety critical crash avoidance applications, and make sure that there is additional spectrum that's made available to support the myriad of applications that we've all been discussing that can be brought to the market if there's sufficient spectrum to support them.
Right, it's a great point. Absolutely, Hillary, totally agree with you. And for us, it's foundational to our autonomous vehicles issues and safety moving forward. So we see the great potential of this technology and look forward to continue working with all of you and working through the United Nations to learn from all the experts throughout the world. But today, I want to say thank you to our distinguished panel. Each one of your presentations was absolutely excellent. And really, I learned so much from all of you. I know all of us participated today really are grateful to hear from you where the technology is going, what the future holds. And we're pretty excited about the future of that. I want to thank Steve and Hillary and Minakata-san and Uwe for their presentations. They did a great job. And thank you so much. I also want to thank my co-chairs of the Intelligence Transport Systems Informal Working Group, Ian Yarnold and Takahashi Nanao-san, for their work and their great collaboration with me. I also want to thank the UN Secretariat at WP29, Francois Gouchard and Melissa Archer, who pulled our work together this morning, this afternoon and this evening for us. This was a great panel and could not have happened without their work in Geneva. So I also want to thank all of you who were able to join us today. Your questions, your participation are so important. We welcome you to come and work with us at the ITS working group at the UN. There's a lot of work that we need to get done. And I think pulling everyone together and your expertise will make us stronger and more effective and promote safety benefits throughout the world. So please join us in Geneva. And thank you for joining us today. With that, this is the end of our panel. Thank you so much.